All right, guys. So what we're going to do today, we're going to go over Earth's motions. So this was the worksheets that I gave you on Friday. So today we're just going to slowly go through them. A lot of the questions, they're regions questions, so they basically repeat themselves just in a different way. So for number one, it's asking you the Coriolis effect occurs as a result of Earth's. So remember, we have Earth. And the Coriolis effect basically says how that the planetary winds are changed due to the rotation of Earth rotating on its axis. Okay, so remember, we have Earth rotating on its axis. We have the south. We have the north. And what happens is that our wind doesn't go in a straight line. It more curves as it's going across Earth's surface. And then the same thing happens in the southern hemisphere, where it goes, basically it veers off to the right. And then when you're looking, okay, because this would be the equator, and you're looking the other way, it veers off to the right again. So for number one, it's going to be A, rotation. So I'm going to put that over here. Now, the next one, it says in 1851, Leon Foucault used a swinging pendulum. Okay, so the swinging pendulum, remember, that's the video that I showed you where you basically have the pendulum swinging and it goes back and forth and it knocks over the little pillars going around it in a circle. Okay, and because it's swinging back and forth and the Earth is rotating, it swings. It knocks down this one, knocks down this one, then it'll keep rotating, knock down that one, and then eventually it knocks down all the pillars, and it causes, after it knocks down all the pillars, that represents 24 hours. So it's a new day, and then they set them back up. So for number two, it's demonstrating how the Earth is rotating. So again, it's rotation. So two is going to be A again, all right? And then I'll correct number one is also A. All right, so number three, the deflection of Earth's planetary winds is an example of, so we just kind of talked about it, how the planetary winds, they go in a way where it basically turns to the right, gets deflected by the rotation. So this effect, instead of just saying, oh, the rotation's changing it, the actual term for it is the Coriolis effect. So number three is also going to be A. The best evidence that Earth's rotation is provided by so Earth's rotation, we're looking at that. Number one, it says the Fulcrum pendulum. Fulcrum pendulum is correct because that's showing the Earth's rotation, but global warming has nothing to do with the actual rotation of Earth. Oh yes, I shaved. Yep. It was getting too warm with the warmer weather. So number two, we got the Fulcrum pendulum, and now you have the Coriolis effect. And like we said before, the Coriolis effect affects and is get affected by the rotation of Earth. The moon phases in global warming, again, the moon has nothing to do with the rotation of Earth. And the moon phases in the Coriolis effect, even though for D, it has Coriolis effect, it still has the moon phases. So number four is going to be B. On the Earth, a freely swinging pendulum gradually shows a change in direction of its swing. So like I said before, it's going to be swinging along and changing direction. And the choices, it says for number five, number one is an orbiting natural satellite. Has nothing to do with this problem. Revolves around the sun. Yes, the Earth revolves around the sun, but it has no effect on the pendulum. The rotation of the axis is going to be the right choice. And then for D, it says an elliptic orbit, which is also rotating around the sun. So it's kind of giving us the big picture, but we're just talking about why this is swinging and why does it change direction as it swings. So number five is going to be C. Number six, the orbiting motion of the Earth is best described as So again, we have the orbit of Earth. It is rotating, and it's going to be rotation. The day of the year as unit of time is based upon motions of. So for this, the motion of time, if you remember, that's the changing of the months, okay? When we go from New Year all the way around, we go through the fall, we go to summer, then we go to the fall. I mean spring, summer, fall, and then we get back to December again. And basically, we have the sun, and where we are going around the sun, okay, so we have Earth, is what time it is in the year. So for this, it's the day of the year as unit of time are based upon the motions of, it's the motion of the Earth. So right here, let's say this is the winter. We go over here. The next season that we get into is the spring. Over here is the summer. And then over here is the fall. Okay? The sun is not moving. But what changes with the time of us that affects us is where the Earth is positioned around the sun. That's what time it is. And then as we go, we get closer to the winter time. As we go, we get closer to spring months, okay? And then for summer, so right now, we're starting basically our summer months. So we're, again, this is not to scale, but if we were to go, we would be over in this area right now. This is where we would be today, okay? Because we're heading into the summer months, and then the summer months, that's going to be, it is June. Then you have July, then you have August, and now you're traveling back through September. So for number 7, it's going to be the Earth, which is B. All right, so if we flip it over, which is the best evidence for Earth's rotation? Remember, Earth's rotation is it's spinning. So the rising of the sun, that is one of the things behind it. But remember, when we thought it was the rising of the sun, we actually thought it was the sun going around. And that was the geocentric system. But now we're in the heliocentric system where the sun is actually in the center of the universe. So it's actually going to be B, the motion of the focal pendulum. Number 9, the Coriolis effect provides evidence of the Earth. And again, same question, just asked a different way. It's going to be the rotation on the axis. So 9 is going to be B. The predictable change in the direction of the swinging pendulum fulcrum would be influenced by the rate of rotation. Again, we're just constantly just asking questions about the Earth's rotation. Number 11, in New York State, which day has an equal period of sunlight and daylight? So remember, when we were talking about, I'm going to make a different picture of this. Okay, so we have our sun in the center. Now we have our orbit going around the sun. Remember, though, the Earth is tilted at an angle. So we have the Earth here, 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 and here. Now that angle is always tilted towards Polaris, which is the North Star. So since it's tilted, not every part of the Earth always gets the same amount of sunlight. So this goes back into our notes. So for this, I'm only going to color in the northern hemisphere. So remember, since it's tilted, here's our northern hemisphere. Here's our northern hemisphere. Northern hemisphere. And northern hemisphere. Now, since it's tilted, it's still rotating. So the northern hemisphere is actually pointed away from the sun when it's on this side of the sun in the orbit. So for this time, the northern hemisphere is not getting as much sunlight. So this is going to be the winter time. All right, this is the winter season. Now, when it gets back below down here, it's still tilted, but since it's facing the sun in a way, it gets the same amount of sunlight. So this is going to be spring now that it gets warmed up. Now you keep going. Our northern hemisphere is actually tilted towards the sun. So this is the summer. And the last one going in, it's tilted again, but again, it's still at an angle where you're getting the same amount of sunlight. So this is going to be the fall. Now, for this question, it's asking you what date would be equal periods of sunlight. So if you remember from the notes, the winter time where the northern hemisphere gets the least amount of sunlight is December 21st. For the summer, when we get the most amount of sunlight, which we're getting close to, we're not there yet, it's June 21st. So at the end of this month, we're going to have the most sunlight. That's why every day the sunset is later in the day. Now, for over here, the fall, it's going to be September 21st. And then for the spring, it's going to be March 21st. So these are the days. And remember it's always 3 months later every time. And the date, it's always 21. Okay, it's always the 21st of that month. So for this, the choice that only reaches out is in New York State, which day has an equal period of daylight and nighttime? They give you December 21st, but like we just said, the north is facing away, so it's going to get the least amount. So that one's out. March, that one so far looks correct. Then we have June. That's when we get the most amount of sunlight. And then it doesn't even give us the fall. It just says none of the above. So the actual answer is going to be B, March 21st. So for 11, it's going to be B. The actual shape of the Earth's orbit around the sun is best described as, so when we were talking about the actual orbit around the sun, it's not a perfect circle, so it can't be B or C, okay? It's a slightly eccentric ellipse, because an ellipse, you have a perfect circle and then a perfect ellipse. It's going to be a straight line. So it's going to be somewhere along this, where it's kind of like an oval. So for number 12, it's going to be A. Remember, you can always pause the thing, but I got to just make some room so I can actually do the equation. So for number 13, it says, what is the eccentricity of an orbit having a major axis length of 100 million miles? So here's the first thing they give us. They give us 100 million miles, and that's the major axis. Now the other thing is the focal distance. So they give us the focal distance. Focal distance equals 10 million. Okay? So what we have to do is we have to find out what the eccentricity is. So the eccentricity, if you go to your reference table, on the front, it says eccentricity equals the distance of the focal divided by the length of the major axis. So since this problem gave us both of those equations, or both those numbers, we have millions of miles, major axis. So that's going to go below it. And then the distance of the foci is 10. So you're going to do 10 divided by 100, and that ends up giving you 0.1. Okay? So the 0.1, that's going to be choice D for 13. This one, according to the Earth Science Reference Table, which planet has the most eccentric orbit? So that's going to be the highest number, because remember, eccentric is a perfect number of 1. So for this, what you're going to do, I'm going to put all the choices on the board. You have Earth, you have Mars, you have Venus, and then you have Saturn. Okay, those are your 4 choices. Now, what you're going to do is you're going to go into the Earth Science Reference Table, okay, page 15, and you are going to find where it says the eccentricity of the orbit. So you have to go to each one of these planets and find out which one has the highest eccentricity. So for Earth, it's 0.017. For Mars, it's 0.093. Because remember, I don't have this memorized, but I know to use the Earth Science Reference Table to find these. For Venus, it's 0.007. And then for Saturn, it's 0.054. So for number 14, it's looking for the biggest number. So we have Mars. That's the largest. So Mars is number, or letter B. Now for 15, it says, according to the Earth Science Reference Table, which planet has the least eccentric orbit? So it gives us the same choices. So now we have to find which one of these has the smallest number. So that's going to be Venus. So our choice for 15 is going to be C for Venus. Okay. So that's the first part of that worksheet. Now, the second part, it gives you a chart, and you're just going to be reading off which ones have the closest eccentricity, okay? So for number 16, it's asking you which 2 sets of planets have nearly the same eccentric orbit. So for this, if you look at them, it's going to be Jupiter and Uranus, okay? So you got Jupiter and Uranus. Because Jupiter, if you look, has an orbit of 0.048, and then Uranus has 0.047, okay? And then for 17, it's asking you to put them in order. So if you put them in order, okay, make sure you always check them off after you use them from the least to increasing. It's going to be Venus, then it's going to be Neptune, then it's going to be Earth, then Uranus, then Jupiter, then Saturn, then Mars, and then Mercury actually has the highest eccentricity of our planets. Okay? Bring it down a little bit. Now, after you get all these, because they're increasing, is there a direct relationship between the eccentricity of orbit and the distance from the sun? So these planets are not in the order that they are from the sun. So for 18, you could just put no. There's no relationship. Okay? Each planet has its own eccentricity, and it doesn't matter how far or how close it is from the sun. All right, so for the last page. And for this, I'm actually going to make some room, so I'm going to erase the notes. But again, you can always pause the answers. It gives you this giant diagram, okay? So we have the sun. Then we have this orbit going around, okay? Remember, it's not a perfect circle because our orbit is a little eccentric. You have your Earth going around. Okay, and just to make it easy, I'm going to erase the actual lines inside. Okay, so that's what they give you first. Now, they actually show the picture in a different way. It actually shows the tilt going this way. So we're looking at the solar system from a different angle. Okay, but we still have the north and we still have the south. And also remember that our equator is moving through, okay? So it says, state the number of degrees that the Earth's axis is tilted, particular to the plane of its orbit. So we're looking at the actual tilt, okay, which it revolves around. So the actual tilt for 19 is going to be 23.5 degrees, okay? Identify the season in New York State during the Earth in Raphelion. So for this, we're looking at it. So we have Perihelion, okay? It's on this side. And then the other one that we have is, so remember, A away, that's the furthest it is. And it shows that because it's 1.52 times 10 to the 8 kilometers. And then on this side, the distance is 1 times 10 to the 8, okay? That's the distance. So we're asking what month are we in, or what season? We're actually going to be in the summer, okay? Because it's tilted and it's facing this way. State the number of daylight hours that an observer in New York State will experience at position D. So position D on this is right here. So this is the fall months. So what we know, if it's over here in this area, this is going to be September 21st. So that's when we have 12 hours of sunlight. And that's how much sunlight we're going to have for that. 12 hours of sunlight, 12 hours of nighttime. And then the last one, 22, it says identify the name of the star that is aligned with Earth's axis above the North Pole. So remember, our tilt is always pointing at the same star, and that star is Polaris, also known as the North Star. Okay. So keep that up for a second. Hopefully it's making sense. Again, I understand that doing this from home, not being able to ask me questions right away is difficult. Do the best you can on that. When I'm grading, I am showing you guys what you guys got wrong. Hopefully you check it. I'm going to put up another PowerPoint today. It's going to be on the sun. So right now we've just learned about Earth's motion around. Now we're going to talk about the sun. And then we're going to get into some of the other planets and the characteristics that make those planets. After that, I'll probably put a little worksheet on that, but keep doing what you're doing. You guys are doing great. And I will see you guys later.